Anything else? Oh, there's a forum tomorrow. It's not a devotional, it's a forum from a macroeconomist. So I'd encourage you to go. Forum speakers always have something interesting and insightful to say. So who'd like to start us off with a prayer? Thank you. Amen. Thank you very much. Does your name start with an A? Evan. What is it? Ethan. Dang it. It's close. Evan, Ethan, that's pretty close. Okay. All right, take a minute and look at these problems, especially number one, but well, they're not numbered. Okay, especially the top one. The second one is really to help you understand, and we'll talk about like what does closure mean, because they use the phrase closure, the word closure a bit in this section. So we'll talk about that. But take a minute and think about these questions. You can talk with your neighbors. And for those that are online, I'm just going to I just turned down the audio in here, so you guys are welcome to talk to each other while you discuss this. So, okay, just take a few minutes.
I did tests. Wow.
I would say with the first one, it is not a subspace, right? Like if the scalar C was negative, then it would be open. Is that what it would be called?
All right. Looks like there's lots of questions about this section. I heard people say that this was oops. There. I heard people say this was a really hard section. It is. This is a big, hard section. Not hard because it's like extremely complex. It's hard just because it's different, and it's hard because a lot of these things we're talking about, we're calling some of the same things you know by different names. So that's kind of the name of the game in linear algebra. Seeing the same thing in 5 different ways. So it's like a 5-dimensional class. You know, we just visited in 5 different dimensions. So I think for this one, let's do closure. I'm not going to do the first one here yet. I'm going to do closure, and then I'm going to talk a little bit about subspaces, spans, column space, and row spaces, and then we'll come back to some of these problems. Okay, try to see if we can get kind of all on the same page. Today's topics that really aren't that interesting. Tomorrow's will be much more interesting. Well, Wednesdays will be much more interesting, and next Mondays will be even more interesting. But this is like setting the foundation for those interesting ones that are coming up, interesting and more applied ones coming up. Okay, sorry about all the text. This is mainly notes for me. So the idea of a subspace is a more abstract version of a span of vectors. So for this class, when you think about a subspace, you can think about a point and a line and a plane and 3 space, or a hyperplane, a 3-dimensional hyperplane in 4 space, which is, of course, it's really hard to imagine. But those are the kind of things we will be talking about when we're talking about subspaces. If you have those in mind, you'll be doing really well. You know, you'll be right 99% of the time if you just think about those things. Subspaces can be much more abstract. I think I mentioned a couple. Yeah, like sound waves. We can think about all possible sound waves as a subspace, and we'll make connections to that on Wednesday on how it makes and how we can use ideas with subspaces to help us make sense of sound waves and build them up and compress them. Or polynomials, we can think about polynomials as subspaces. But that's not what we're focused on in this class. We'll just focus on some pretty basic ones, which is the kind of geometric ones we've been dealing with, mainly lines and planes and hyperplanes. So you would have read about a subspace is defined with 3 things. Is this a new board? Did we have this line in here last time?
No, they changed the board like Thursday or Friday.
Wow, okay. Well, we'll see how the new board works. So a subspace defined by a set of vectors, u1, u2, etc. But it needs to have 1, 0. The 0 vector is in the subspace. We'll call this subspace S, just for short. Okay. Technically, on the slide, it doesn't technically have to have 0. It just has to be non-empty, and it's easy to look and see if 0 is there. As long as it's non-empty, you can then show that 0 has to be in there. But all subspaces have the 0 vector. So 2, I don't know what order they do this in, but if U is in S, then C times U is in S. Okay? So you can take any vector in there, you can take a scalar multiple of it, and it will also be in there. Okay? So the word mathematicians use for things like this is it's closed. So this is closed under scalar multiplication. Okay, we'll come back to closed in a second. And if U and V are in S, then U plus V is in S. So that's an element of, or is in symbol. So, this is, it's closed, mathematicians would say it's closed under addition, okay? So let's go back to the slides. Thanks, let's go up to the first slide. So on that second one there, it says, which of the following sets of numbers are closed under addition, subtraction, multiplication, divisions, and powers? So whole numbers, if we take any two whole numbers and we add those whole numbers, those two whole numbers, do we get another whole number? Yeah. So 2 plus 3, it's 5, it's in there. 113 plus 127, you add them together, you get something, it's still a whole number. So whole numbers are closed under addition. Are they closed under subtraction? Give me a counter example. Why aren't they closed under subtraction? Okay, he said 1 minus 2 is a negative 1, and that's not a whole number. So any two whole number, if I subtract any two whole numbers, I might not get a whole number. I could get a whole number, but I could get a non-whole number. What about multiplication? Are whole numbers closed under multiplication? Yeah, if you take any two whole numbers and multiply them together, you get another whole number. So are they closed under division? No. What's an example? Sydney? 2 divided by 3. Perfect. It's 2/3. It's not a whole number. Okay. So integers, they are now closed under addition and subtraction. If you take any two integers and subtract them, you still get an integer. You can add them, you get an integer, and multiply. Like multiplication, they're closed. But are they closed under division? No. So you can keep adding numbers to the set to get it closed under more and more things. Basically, what happens is kind of the history of your math schooling right here in 5 lines. Right, you started with counting, and then you went to counting and addition, and then you went to subtraction and multiplication and division, and then you had to start worrying about fractions, right, and then roots and complex numbers and all sorts of stuff. But rational numbers, they're closed under addition, subtraction, multiplication, and division. Okay, so they're closed under all 4 of those. You'll always get a rational number if you take any two rational numbers and do any of those operations. Q not being 0, you can't take Q as 0. But what are they not closed under? They're not closed under powers. Like the square root of 2 is not in that set. So then you have to add more things to get all the powers, and that's not even all the powers. That's just the powers, the powers of positive values, and the opposite of those. And complex numbers you have to add because you don't have the roots of negative values. But okay, are we better on closure now? What closure means? So a subspace, you can summarize all of this about subspaces. It's a set of a subspace of a set of vectors is all possible linear combinations of those vectors, where the linear combinations, we already have an idea about linear combinations. They are scalar multiples and addition. We don't have to talk about subtraction, because if you have scalar multiples and addition, you get subtraction. Because I can multiply v times a minus 1 and then add it to u, so I get u minus v, stuff like that. So, so a subspace is any set that's closed, that's non-empty, and the book just has us find the 0 value, it's 0 vector, and it's closed under linear combinations. Linear combinations captures both of those. Okay. So with that much, let's go back to this slide. Now, let's look at number 1. Are vectors in standard position in the first quadrant a subspace of R squared? So do they contain the 0 vector? And are they closed under linear combinations? Can you do both of these and end up in the still as in one of those vectors, as one of those vectors? So think about that for a second. I know you have already been thinking about it, but now you might better be able to think about it. Think about why this is true or why it is false. So I drew a bunch of vectors there that might be in this, that are in this this set. The question is this set a subspace? So I wrote down drew a bunch of vectors in standard position in quadrant 1. Is the zero vector in here? The technical definition is this is all x and y where x is greater than or equal to 0, y is greater than or equal to 0. Is the zero vector one of these vectors? Yeah, I can have x equals 0 and y equal 0. I'm just fine. Got that point there? Great, got the zero vector. Okay, is this closed under scalar multiplication? I heard some yes and some no's and some I don't knows. Okay, let's take a vector. Okay, so suppose I take this vector right here. Okay, if I double it, is it in the set? Yeah. Triple it? Million times it? Yeah. Multiply by 0? Multiply by a -1? No. So if I only had positive scalars, I'd be okay. But a negative scalar here, which we're including scalars of all real numbers. So C is a real number, so can be positive or negative. So no, this is not a subspace because it's not closed under scalar multiplication. So we don't have to check this one, but we will for fun, just to help us better understand it. So take 20 seconds, talk to your neighbor. Is this set of vectors, is it closed under addition? So if you take any two, then if you take any two and add them together, do you still get a vector that is in this first quadrant? It starts here and goes in that first quadrant. So take 20 seconds, talk to a neighbor. All right. What do we think? Thumbs up if we think it's closed under addition. Thumbs down if you think it's not closed under addition. Thumbs sideways if you don't know. Okay, lots of thumbs up, a couple thumbs down. Okay, so someone that put their thumb up. Do you want to volunteer and explain what you're thinking? You never input. Rochelle? Okay, so you're thinking like all the entries are positive. Right. So you're thinking, when you say positive vector, you're thinking each entry is positive.
Yeah, I guess that was not good. In that quadrant, I imagine when we add two vectors that are just in that quadrant, they'll still be in that quadrant.
Okay, so are you thinking geometrically? Okay, you're thinking like, well, if I've got this one and then I add maybe that one to it, then I'm going to get a vector that's, something like that. That's still going to be in there. I can't start at the end of any of these and get down below here. right? By adding a vector, because then that means my vector would have had to be in this third quadrant, or was that the first one? Fourth quadrant. So, but how do we know? How do we know for sure there isn't two vectors in there you can add and not end up here, here, or here? We don't want to check all infinitely many of them. Philip? Okay, I like the way you said that at the end. It's impossible to add a positive entry with a positive entry and end up with a negative entry. So that's true. So if I take any two vectors here, if they're in this set, I've got x1 and x2 have to be 0 or greater, y1 and y2 have to be 0 and greater. So I add them together, I get x1 plus x2, y1 plus y2, and then using the properties of adding positive, we're adding values that are 0 or above, which is real numbers of 0 or above are closed under addition. So yeah, that will be in the subspace. So yeah, it will be in this set. It's not a subspace, but it'll be in that set. So the one we've been experimenting with, it does have the 0 vector. It is closed under addition, but it's not closed under scalar multiplication. So it's not a subspace. All the subspaces we deal with, in fact, there's a theorem that you would have read about. All subspaces are spans of a set of vectors. We can think about all subspaces as spans, and it turns out we can think of all spans as subspaces. I think that's the point. Yeah, that's kind of the last point. We're going to be, a lot of the subspaces we're going to be talking about will already have vectors like we've been thinking about, column vectors, and we'll be looking at the span of column vectors. Sometimes we'll look at row vectors, a span of row vectors. But we'll talk about that more in detail in a second. So let's talk about columns, okay? So what is a column space? So two of the main subspaces that we're going to talk about. Turns out every matrix has 4 standard subspaces with it. Okay, we'll hit 2 today. So the column space of A, the row space of A, the null space of A. So that's going to be a topic for tomorrow. And what's the last one? It might just be the 0 space, but I think that's the best way to describe that last one. So we're going to be talking about row space and column space. You have already been working with the column space of a matrix, because the column space is just the span of the columns of a matrix. Okay, so here I have our peanut butter and bread, fat and protein example. What's the column space of that matrix? Well, it's all possible combinations of the servings of peanut butter and the servings of bread. So I can take it, how many servings of peanut butter, how many servings of bread am I going to take? Like any combination I take there, I'm going to eventually get some values of how much protein, how much fat I have. And so the column space is all possible protein and fat combinations that I can get by taking linear combinations of peanut butter and bread. So that has a nice interpretation to it. Okay, if they're linearly independent, if these happen to be linearly independent, then I'm going to span the whole protein and fat space. That would be the subspace. You give me any protein and fat combination, and I can tell you, I can find how many servings of peanut butter and how many servings of bread it would take to get that combination, if they're linearly independent. Okay, these are in this case. Okay, so column spaces, they have nice interpretations often. So that kind of tells you your possible goals that you can attain in a context like this. Right vector multiplication is a way of representing that column space. When I write this matrix times xy, then that way we can interpret that is exactly, oh, that's x columns of the first column and y columns of the second column, and I add those together. So that is this. We can interpret this as, oh, that is the column space of that matrix. Okay. And there are natural questions about the column space, or natural questions about lots of subspaces of a matrix. But if I have a certain vector, like B, is it in the column space? And this is going to look familiar. We did this more than a month ago, so we just didn't talk about it as a column space. Okay, so to think about, is it a certain vector B in column space of A? That's the same as the system AX equals B. That's the same as just a system of equations that you would have run into like however many years ago when you were doing algebra. So we just didn't think about it as a column space and B as an element of that column space. But to answer that question, then we can go back to AX equals B, and we can augment and row reduce with our matrix A and the vector B they give us. Okay, that answers the question. Is it in there? How does it answer the question? Well, if there is a solution to that system, then B is in that column space. Okay. And describe the column space of A. So that might be, the column space might be all of R2 or all of R3 or all of R5, but it might be a subset of that. It might be a plane in R5 or a hyperplane with 3 dimensions in R7. Who knows what it could be? And to figure that out, we just augment it with any X and Y. Like what possible X's and Y's can I get as linear combinations of these? And there was an example on the video where we did this in 3 space. Okay, questions so far? I forgot to ask about what questions you had from the reading in the video. I should have started with that. Yes?
So the column space of A has to be a subspace?
So the question is, does the column space of A have to be a subspace? Yes. So the column space of A is a subspace. The column space, row space, and null space of A, they're all subspaces. Null, again, we'll talk about it next time, but yeah, because the column space is the span of a set of vectors, and every subspace can be written as a span of a set of vectors. So if you can write it as a span of a set of vectors, it's a subspace. So it has the 0 vector, so we can talk about each of these 3 things. Does it have the 0 vector? Yeah, because I can take 0 of the first and 0 of the second, or a zero amount of all of the columns, and then I'll get 0 out. So it has that. If I multiply by a constant, one of those, it's still in the column space. And if I add 2 columns, I'm still in the column space, because the column space is defined as all the linear combinations, and these are just the operations we do to get linear combinations. So good question. Okay, other questions so far, or questions from the reading, or videos that we haven't got to? I know you guys have questions, so I know you might be so lost you don't know what question to ask. That is understandable. How many of you feel that way? Do a thumbs up if you feel that way. Don't be shy. Okay, so a few of you. Okay, thanks. Well, let me do more, and then we'll come and do some problems. Oh, flip. So I want to talk about why do we always use column vectors, because we're going to start talking about row spaces and row vectors, and we haven't really done those very much. So really quickly, I wanted to answer this big question, like what's the difference between row vectors and column vectors? So there's not a lot. Any point in R3 you can write as a row vector or any vector in R3, you can write as a row vector or a column vector, okay? There's just lots of nice advantages using them as column vectors. But we can choose to write them either way. So some of the reasons why we write them, it's a little more natural to think of a right matrix multiplication, A times X, especially when we think about transformations where A is a matrix doing a transformation on the vector. This makes a lot of sense because we kind of think left to right, so like A transforms X. And if that's the case, then X needs to be a column vector. And the meaning of A times X we can think of as a linear combination of the column vectors where the entries of X tell us how much of each of the columns we're taking. And so here we're talking about column vectors again. The result of AX is also a column vector. It's easier to match up here to compare vectors if you write them this way than this way. Because here you can be like, oh yeah, 1, 4, 2, 8, 3, 12. Here you're like, okay, which one does that one go to? And like it's just harder to write. And it's more compact. You can put a lot more on the line if you write your vectors as columns than you can with rows. So just lots of those reasons make it so we work with column vectors a lot, but you don't have to. So row space. I want to get rid of this. Yeah, it's a little better. So the row space is defined like the column space. Column space is all the linear combinations of the columns of a matrix. Row space is all the linear combinations of the rows of a matrix. Okay. One of the reasons we don't use row space a lot, or don't use row vectors as much, is that in a context, matrices often have one space that's really easy to interpret, and that's the one you're using it for, and the other space doesn't make a lot of sense. If we're just dealing with an abstract matrix, then it doesn't matter. But I put our peanut butter, bread, fat, and protein up as an example. So when we think of linear combinations of the columns, we get all possible fat and protein combinations. But what if I take all possible combinations of these rows? So I can still represent it as a multiplication. I've done that down here in the lower right, or the lower left. So if I take a row vector, x, y, and multiply it, here I'm doing left multiplication instead of right multiplication, then that is x times the top row, y times the bottom row, and I add them together. So I've written that out a little above that. So talk to your neighbor. Tell me what I get right here in these entries. The slash s is per serving. So here this is all possible fats per serving oh, this is actually not per serving anymore, is it? It's just fat and protein. So maybe I should delete those per servings. But here it made sense going this way. Like this is how many grams of fat per serving and how many grams of protein or fat in bread per serving. And then I multiply by the number of servings and I get total fat and total protein. What do I end up with right here? So try to use the context and the meaning of those to figure out what we end up with in that row vector. All right, has anyone got anything insightful for us? Anyone been able to make sense of this one over here, this row multiplication, this row linear combination of the rows, and what that, how would we interpret the thing that we got from that? Oh, yes, okay, I want to hear it. Good. So you're saying, is it a how much peanut butter and how much bread thing that I have instead of how much? You're saying, hey, maybe you're starting with fat and protein, and you're figuring out how much peanut butter and how much bread you need. Okay. I don't think that's quite the interpretation. So that is a nice. That's a thinking about inverse multiplication there. So about what the inverse matrix would help us with. So there is some good thinking there. I just don't think it matches up to this one. So thank you. Yeah, the units here are crazy. Like, it makes sense to add grams of fat per serving and grams of fat per serving, right? Or grams of fat and then grams of fat. That makes sense going this way. But when you're adding like a multiple of 15 and a multiple of 8, you've got like fats plus proteins. Like, what is that? I mean, like stuff. This is grams of stuff. I mean, it's just harder to interpret, like what you get that way. And that often happens in contexts. And so we usually write the matrix the way where combinations of columns make sense, and we just focus on that. So we often don't have to handle both. Sometimes they do have nice interpretations. Yes. Yeah, all right, because you're thinking about like X as, X seems to be associated with fats because it tells me something about the grams of fat that I have in both of these, right? So, so I have X of the fat vectors and Y of the protein vectors. And I don't know, I have to think about it more. I thought about it before and I couldn't come up with something slick. So, yeah, keep thinking. You guys can bring some more insight for me. Yes? So get rid of the, yeah, so maybe rewrite the quantities here instead of, maybe I shouldn't be thinking about them as fat per servings of peanut butter. Maybe I should think about them as yeah, like the inverse thing there. And so I have, yeah, something of peanut butter per fat. Yeah, that might be able to get us something. And that's probably what you guys were thinking about in the back, right? Yeah, I see where you were going now. So nice. Okay. Okay, quickly, we haven't even done some examples, but if they give you a vector and say a row vector and say, is this in the row space of A, then there's a couple things you can do. What I like to do is I just turn it into a column space problem. Just transpose your A and transpose your B and turn it into the kind of matrices you're used to row reducing. But you can do it this way. You can take A and then you augment it at the bottom. And then you row reduce. And if the bottom row becomes all zeros, then B is in the row space of A. So, and I would suggest you do this also if they, if you're trying to describe, oh, I didn't change that to row space of A. That should be described the row space of A there. Then take A transpose and augment it with your x, y, z vector, or x1, x2, x3, x whatever vector, and then row reduce this to see what you get. So, okay. I wish we had a lot more time to talk about this. Let's go back and look at these problems. So one of these I think was right from the reading, or right from the video. So let K be the set of all vectors V in R3 of the form, so V is any x, y, z where y equals x and z equals x cubed. So take just a minute, see if you can work on this. You can also work on 2. Show that the set of vectors on the line y equals a negative 3x is a subspace. So there's 2 problems, typical kind of homework problems with these. How do you go about doing that? You don't have much time to work on it, but I'm going to let you guys work on it a little, and then we'll go over it as a class. Okay. Let's work on one. So I started writing down some stuff on the board here. So V is any x, y, z where x, y, and z have this relationship. Y equals whatever x is. So I just replaced y with x. Z is the cube of whatever x is. So I just replaced it with x cubed. This is a lot easier for me to see. And this is a nice strategy when they give you that information like that. Try to get it all in terms of 1 or 2 variables, as few variables as possible. Okay. And then I plugged in at x equals 1. I get this vector. At x equals 2, I get this vector. There's a couple of different ways we can show that this is not a subspace. I should have said, is the 0 vector in this? This is in V. Yeah, at x equals 0, this becomes 0, this becomes 0. So the 0 is in there. The 0 vector is in there. But the question is it closed now under addition? Is it closed now under scalar multiplication? If either of those are false, then the whole thing is false. We'll do it both ways. Hey, if 1, 1, 1 is in there and it's closed under scalar multiplication, give me another vector that better be in there. I'll give you another vector that better be in there. How's that? So 2, 2, 2 has to be in there. Right? Because if 1, 1, 1 is in there, I can multiply any vector that's in there, if it's a subspace, by any non-zero scalar. And it needs to be in there. Well, 2 is a non-zero scalar, so I get 2, 2, 2. Is 2, 2, 2 of the vector of this form, x cubed? No. Nope, you can't pick an x. There's no x to satisfy that, so it's not closed under scalar multiplication. Here's two vectors, because for this to happen, sorry, let me go back. For this to happen, x has to equal 2 here, right? But if x equals 2, then that last one is 8. It's not 2. So here I picked two vectors. You can pick two vectors to show that it's not the case here, that they not being closed under addition. If I take these two vectors and add them, I get 3, 3, 9. And that's also not of the form x, and x cubed, because x cubed, that means x would have to equal 3. But then x cubed equals 27, which last I checked was not equal to 9. Okay, so this would prove that it's not a subspace because it violates property 3 there. Okay, questions on this? Yes, Ethan. Those bigger ones will come next time. The book doesn't motivate this very well. It just comes out and says, hey, subspaces. It does talk about dimensions. It will help us talk about dimensions of things, but things that have subspaces, we can find bases, and bases are incredibly powerful and important. So, but if it's not a subspace, then we don't even bother trying to find a basis for it. So, but that's one of them. Good question. I love that question. Okay, number 2. Michelle, do you want to go back to the slide and we'll find out what. Show that the set of vectors on the line y equals a negative 3x is a subspace. Okay, so set of vectors on this line. So they're all vectors of the form x, a negative 3x. Okay, so first, so I need to show is the 0 vector in there. So the 0 vector is, I'll just call it V again. I'll call this one V. Okay, so V is the set of all vectors like that. So the 0 vector is in V. Let x equal 0. Then you get 0, a negative 3 times 0, which is 0, 0. Boom, check. So the 0 vector is in there. How about is it closed under scalar multiplication? Well, I'm going to take a random one here, x, a negative 3x, multiplied by c. Is that still of the form this? Well, let's do some algebra and see. A negative. Cx, c times a negative 3x. And then cx, I'm going to pull that c in and that negative 3 out. And look, that is of the form something, and a negative 3 times that something. So check. And how about closed under scalar, not scalar multiplication, closed under addition? Well, I'll take x1, a negative 3x1, plus x2, a negative 3x2. That is x1 plus x2. You do the algebra here, you get a negative 3 x1 plus x2. Is that of that form? Yeah, it's the form of something as your x, and whatever's in your x, it's a negative 3 times that something in your y. So check. So if you're trying to show it's not, you want to find a counterexample, like we did over here. If you're trying to show that it is, then you need to go through. 0 is pretty easy, but here it usually requires some algebra to do some manipulation to show that a scalar multiple is of that same form, and adding 2 different ones still of that same form. All right. Great question. So that question was, if we're trying to prove that it's not, do you just have to disprove one thing? Yes, you just have to disprove one thing, and then you don't even have to care about the other ones. All right, have a great day, or rest of the day. Don't forget the homework's up over here.